Okay, so thank you very much. Thank you very much for the introduction and the possibility of giving a talk here. It's really a pleasure to have lots of collaborators here, to meet a lot of people here in Vienna, where I am now, so I cannot say it's the first time to be here. But it's really a pleasure. It's actually the first time I talk here at the ESI. And so today I would like to continue somehow the topic which was introduced by Sebastian Hensel yesterday. And in particular, I would like to add, let's say, a further step. So Sebastian talked about the Mullins-Sekerka problem. What I would like to say is, and to think of, is what happens if we take into account also bulk fluids. So if we take if you assume now to be in this context, because I really like the applications to biology, if you assume to consider a cell can be considered as a kind of a surface which is immersed in a fluid, so it has an external fluid and it has an internal fluid. And of course, the two fluids are very different. You have an intracellular cytoplasm, which is specific with specific proteins and a specific structure. And outside, of course, you have the extracellular matrix, or as you want to call, but of course, it has many different properties. So it's perfectly interesting to see what happens if we consider that, if we assume that this surface evolves through a Mullins-Sekerka equation, but of course, what happens if the fluid then now have an interaction with this surface. And of course, the interest is the fact that the cell changes shape. And so this is why I like this model for the cells, because a cell can intrinsically change very much the shape. And so, of course, kind of modeling of a free boundary problem is perfect. Of course, this is let's say, the first step. The best would be adding some extra elasticity properties and so on. But let's say that already Mullins-Sekerka is already a good starting point, especially from the point of view of weak solutions. So the model is quite simple indeed. We have, as Helmut presented some days ago, so we consider two fluids, one which is inside our cell. You have to imagine that omega minus here is the internal part, is the cytoplasm, is the cell. And outside you have omega plus, which is this extracellular part. Of course, we have the usual characters we have seen many times. So we have chi of t, which will be the characteristic function of omega minus. And then we will have, of course, the other quantities as the normal, which here we will have two normals. We will have one normal, which is the one associated to the interface, which is called n here. And then we have another normal, which will be the one of the container, because we will have, and we will introduce also capillary energy to take into account the boundary contact angle condition. And then we have the normal velocity v and the mean curvature, of course. And then the new part, which was also introduced by Sebastian, is this, what I call U bar, which is the chemical potential. And this is what is basically, let's say, in the model will be harmonic inside omega minus and omega plus. And as Sebastian said, is a kind of extension of its value at the interface, extending harmonically inside omega minus and omega plus. So the model is this. This is exactly as Sebastian represented up to the addition of an advective term. This blue term is the effect of the advection, because of course you have a fluid inside and outside, which somehow tries to transport our surface. But of course, we don't assume that we have a simple transport problem, as for instance you saw when Helmut's talk, when you assume an approximation by Allen-Kahn equations, and you assume that the mobility vanishes with epsilon. There you would get an equation where you would only have the blue term, so a pure transport problem. Instead, here the mobility has to stay constant, so it cannot vanish with epsilon in the sharp interface limit, and it allows to give this problem. Of course, here, as I will show afterwards, we are not talking about a diffuse interface version like Allen-Kahn, but it will be Kahn-Hilliard. In this case, so we also have a condition for contact angles. This means basically that at the angle, so at the, let's say the contact line, so when our surface touches the boundary, there we will see a constant contact angle of this angle gamma, which is constant, which has to be assumed fixed and constant. And then we have the nice part, the additional part, which is the bulk Navier-Stokes equation. We consider so two fluids, which are, of course, Newtonian, incompressible. We also add a no-slip condition for simplicity, so we assume that our boundary, the velocity is zero, so it's completely, does not change the contact angle, of course, because it doesn't interact with the contact angle condition. And then we have the usual condition, also Helmut presented, which is the relation of the normal jump of the stress tensor associated to our fluid with the surface stress, the surface tension, which is associated, of course, to the mean curvature times the normal at the interface. Other two terms, of course, as I said, we want to consider difference of fluid which can be very different from one inside and outside. So we consider fluid which have a different density. So this rho of chi is a density which is basically linear combination of the two. So where we are inside, we will have ρ1. When we are, or better, when we are inside, we have ρ1. When we are outside the cell, we will have ρ2. And the same for the density, for the viscosity. So we also have a viscosity depending on the local phase. And of course, notice that the interesting fact is that what I called here as U, which is the harmonic function inside the cell and outside the cell, is here acting an important role inside the equations. Of course, due to the Mullins-Sekerka problem, we have seen by Sebastian that the mean curvature coincides in some sense with the trace of this U bar. So the chemical potential has to coincide with the mean curvature on the interface. Not only this, but we also have another action which is related to this strange object here. This is an extra flux, and this is associated with the difference in the densities. So since we have two different densities inside and outside, we pay the price that somehow the density does not follow, let's say, the standard continuity equation, but it has inside an internal effect due to this transport term, which is reflected here in the Navier-Stokes equation of this J theta, which is associated to the variation of the density in time, so the evolution of the density. Note that it depends on U bar again. So here again, we have a non-local interaction due to the presence of this U bar. Then this is exactly what I was telling you. Where does it come from? It is from here. So here, this is the famous model by Helmut Harald and Günther Grün in 2012, where here you see that we have the diffuse interface version. So we have that let's say the surface tension is here substituted by the Korteweg force, which is the term which we expect will be the surface tension. Then we have Cahn-Hilliard equation. Note that, as I said, we don't expect any coefficient in front of the mobility. So the mobility has to be constant independently of the thickness epsilon of let's say, the diffuse stripe. And then we have Cahn-Hilliard equation, the standard equation where we have the Laplacian and we have the double web potential. And note that, again, you have this object, which is, I would say, this is the most interesting characteristic of the model, of the AGG model, which is the presence of this quantity, again, as before, as it's exactly the same definition, but the only point is that now U bar, instead of being the first variation of the perimeter, it will be the first variation of the Cahn-Hilliard energy, of course. And so there are even rigorous results showing this connection between diffuse and sharp interface. This was done by Helmut and Daniel Engler in 2016. But of course, this technique is based on chance results, which give, of course, the existence of a weak solution to the same problem I mentioned before, so the Navier-Stokes Mullins-Sekerka. But of course, it's very weak. So we have a very weak solution where we don't even able to get the Gibbs-Thomson law. So, I mean, it's a notion of solution that is not completely satisfying. And so the idea is that we want to give a weak solution in, let's say, with more information, which keeps more information concerning the regularity and some energetic properties. Now, again, of course, we all know, you have seen many times that this problem is a gradient flow and can be considered, so of course, it preserves the mass, and it is also a gradient flow, of course, if without the velocity. So if you don't assume the velocity, Mullins-Sekerka has to be considered a gradient flow. Here we have a modified problem, so where the energy dissipation, here I wrote it as an identity, of course, formally, but you see that you have also the kinetic energy and the dissipation due to the part, let's say, the stress tensor for the fluid. Note that in the energy, I have both the two contributions. So I have a contribution of the perimeter inside our domain, omega, and also I have a contribution of the boundary. This is the contact angle condition, where this is standard. It was introduced by, I think, Stenberg and then Modica. And so we know very well how this energy behaves. We all know that this energy has good lower semi-continuity property with respect to L1 convergence. So this energy is very well behaved. And then it's perfectly feasible then to expect that we can use let's say a gradient flow approach to the problem, at least with the velocity, which is when it is equal to 0. Let's now see what happens if the velocity is not 0. Because again, we have a very similar structure. Because if you now define f of t as to be a modification of the energy, taking into account this nice functional, which is basically the normal velocity times the chemical potential u, you can observe that formally you can rewrite the equation here as it is. So we have the time derivative of a kind of energy equal to minus this, in this space h minus 1, some kind of total time derivative. This dt bar is, of course, the total time derivative. So you have to assume that your set chi, so your characteristic function, is advected by your normal velocity of the flow, which is our v. Of course, in the case where v is 0, you retrieve the original gradient flow structure. And this is interesting because if you keep in mind what I said about the gradient flow, this kind of modified gradient flow, you can expect that somehow we can keep the gradient flow the gradient flow structure and the minimizing movement approach also for our problem. Now, let us see the results which were already obtained, because of course Helmut, many years before the sharp interface result, was able to obtain a result in collaboration with Matthias Röger about the existence of a nicer notion of solution. This is heavily based on the results by Schätzle about the possibility of obtaining this Gibbs-Thompson law, and of course by the most important property which was obtained in a separate work by Röger is concerning the mean curvature vector, because Röger was able to observe and to find that if assumed to have a family of variables which are supported which contain, let's say in their support, they contain the reduced boundary of let's say they contain our interface gamma. If we have this, then you can observe that of course, we have to assume that all these variables have admit a mean curvature vector, so they have bounded first variation. But if they admit a mean curvature vector, if you restrict your mean curvature over this set, this is always coinciding. So we can say that the mean curvature vector associated to this family of variables whose support contains this set is intrinsic, because it depends only on the set. And so this is why here, actually, we can also rewrite this h as to be exactly, if you take this h and you multiply scalarly with this quantity, so the normal at the interface, you get a quantity that does not depend on the variable, but only depends on this set. And this is very interesting because this allows to get exactly the Gibbs-Thompson law, exploiting Schätzle results in a very tricky way, and it was observed by Röger. Using this result, even in this coupling, Helmut and Röger were able to obtain this identity. Nevertheless, this is not enough, of course, because we need much more. Because, for instance, Helmut and Matthias Röger didn't treat the case with different densities. Okay, of course, the model came also afterwards, but the case so with different densities was unaddressed, and was never addressed after that, as far as I know. Then the other point is the lack of a weak formulation for constant contact angle condition, because at the time they treated the case with no contacts, so they assumed that either to work in the torus or somehow assuming that their bubble does not touch the boundary. And then the lack of an energy dissipation inequality. This point is very important because we have seen many times that now there are these new approaches with relative entropy. And so having an energy inequality, an energy inequality also for this problem, which would mean basically that our solution is a kind of Lerehoff solution in some sense, plus the Mullins-Sekerka part. is very important because it gives us the hope that we get a weak strong uniqueness principle. And so we aim at solving these three issues with a new notion of solution. Of course, we don't construct it from scratch because Sebastian and Stinson already prepared the ground for the Mullins-Sekerka equation, the Mullins-Sekerka flow. And indeed, what they were able to do is exactly considering this energy, so the Mullins-Sekerka energy, and let's say this energy where we have also capillarity conditions, so we have a contact angle. And they were able to observe that as long as we pay the fact that we have to consider now two potentials. So instead of considering only one potential, we need to consider two. One is related to the mean curvature, and it is what is called, let's say, curvature potential. One is related to the evolution of the chi, and this is the kinetic potential. If you admit to pay that these two potentials might be different, of course, if you have a smooth solution, they will coincide, but a priori for weak solution might be different, then we can get a sharp energy inequality. And now we want to address the similar problem, but in the case of the presence of an advective velocity field. How can we do? Well, what we were able to obtain is that, again, we are able to construct a curvature potential associated to the mean curvature. So this gives the Gibbs-Thompson law, also in our case. What is different is that now we have a kinetic potential, which is not associated anymore to the time derivative, the partial time derivative of our chi, but is associated to the total material derivative. So we have a kinetic potential which somehow encodes the evolution, the complete evolution of the total material derivative. And using this, of course, you can expect that in the energy, in the weak formulation, let's say for the Navier-Stokes equation, you will have a nice difference because now this famous J tilde, as I told you, is related to the evolution of the density. And the density, the time derivative of the density is, of course, associated to the time derivative of chi. And so here we will use the kinetic potential, the one associated to the velocity, the evolution. And indeed, you see that here you have u, and u is the kinetic one. Instead, in the blue part, we have the curvature, because this is a surface tension, and surface tension is associated to curvature, and curvature is associated to a curvature potential. And so here we have W. So this is very nice because you see in the same equation, you see the action of two different, possibly different potentials, which of course, we also have a consistency principle which says that if we have a solution in this way, then the two potentials will of course coincide. But in principle, with this notion, they might be different. And then we have what we want, the energy inequalities. Notice that we are even able to get separately the energy inequalities. This is a characteristic of the Mullins-Sekerka because we have enough regularity to write this scalar product. If we had, for instance, let's say a mean curvature flow, this quantity cannot be actually computed because we don't have the gradient of W. But in this case, it's perfectly fine. We can write so both equations in which you see that Navier-Stokes is a standard Navier-Stokes up to the presence of this perturbative term, which is exactly the same up to a change of sign of the Mullins-Sekerka part, which is, again, you see the action of the two different potential, curvature here and a kinetic potential. And again, if you sum up the two, you will get a total energy inequality like a Lerehoff solution. So you will obtain the desired Lerehoff, in some sense, let's say, where Lerehoff weak solution plus the energy related to Mullins-Sekerka. So just some words about the technique. What we did is somehow use the idea of this minimizing movement scheme, but applied with a time discretization of the total material derivative. So this was already introduced even by Pironneau in 1986, I think, and then it was used again for trying to give a variational approach to Navier-Stokes equation in Gigli and Mosconi. But here, let's say, as far as I know, it's about these geometric flows is the first time it has been used. And the idea is here is that we want to discretize this total material derivative introducing a flow map. So assume that you have a velocity field which is not depending on time, so you fix the time at fixed time, so you have a velocity field, you assume to construct a flow map associated to this velocity, and then instead of taking the standard Zn minus 1, so the time derivative, the step minus the previous one, you take the step minus, you take the step, the previous step is composed with this flow map evaluated at time minus h. In this way, you can reconstruct it by some change of variables, basically, and you see that this is exactly the definition you give of the total material derivative. You take the pullback of your function, you take the total time derivative, and then you get the push forward. And this is exactly what you do here. Pullback, total time derivative, and push forward, and then you go back. So this is then another way of seeing this structure. This is why it should converge to the right object. And then we exploit this gradient flow-like structure. We do minimizing movements, and now we also use minimizing movements with the Giorgi interpolant. This was already introduced by Sebastian and Garcke in their paper. What we do is adapt it to the case of an evolution equation of the presence of an advective term, which is not a priori obvious. In particular, what is not obvious is that this composition, as I told you, with the flow map, has to depend on T. Of course, for the ones maybe who are not familiar with the Giorgi interpolant, the Giorgi interpolant means that assume that you have your standard minimizing movement, so you have n steps. At each step, you have your discretized variable. What the Giorgi propose is that instead of using only this, we make let's say a finer interpolation between each step. So you have from step 0 to step 1, you also have a continuous of interpolation between 0 and 1, and 0 and h, and so on. And inside this continuous interpolation, you construct the minimizing movement. So you have a continuous variable in t, which interpolates between the discrete times. And note that we need to make this t, which is this continuous variable. This is only for the first step, of course. You have the dependence on t, of course, here, but you have also to put a t also in the flow map. And if you do like this, you have here what I found. When I saw it the first time, I thought it was a real magic, because then the nice thing is that if you take if you assume to take your minimizer, assume to have, okay, a measurable minimizer, so you through a measurable selection principle, you can find a measurable minimizer. Then, measurable in time, I mean, strongly measurable in time. Then you take your minimizer, you evaluate your functional, you try to minimize on that minimizer. What you get is this quantity, and you take the time derivative. What you observe is that taking the time derivative of this gives again this term, which is very similar to this up to 1 over t. You see that it's very similar. And then you get this term, which is exactly the term we expect from the energy. So you see that basically up to the presence of this flow map, this is exactly what I told you before, is the normal velocity times let's say, the curvature potential. Now that we have this nice structure, we have to identify our objects. Of course, one potential will be continuous in time, and we build this, and this is the curvature potential associated to the Euler. You compute the Euler-Lagrange equation, so to make inner variations, and you get you associate the mean curvature to this potential, and then you have this. Of course, this is sampled because then you will have to integrate in time, and so this will be evaluated in discrete time. So you will have a potential which is discrete and a potential which is continuous. Then, so what do you do? Now that we have a minimizing movement step, so we have imagined the step from 0 to h, we have a continuous variable in w, which is the curvature potential, and we have a discrete quantity, u1h, which is evaluated at step 0, let's say. Then you use these quantities to update your Navier-Stokes equation. So you solve Navier-Stokes. Of course, you cannot discretize in time Navier-Stokes, or better, it would be more complicated because, as I told you, we need to use both the potential, and one of the two is continuous. So either you sample this quantity and you do the Navier-Stokes discrete, but this would be complicated because WH of t does not have good properties in time. So, I mean, it's always integrable in time. So we don't expect useful properties. What we do is the opposite. We work with a continuous Navier-Stokes equation problem where we solve this of course, we need a regularization from the point of view of the operator. We will, for instance, we could use a higher order operator for let's say, instead of using a Laplacian, we could use a B-Laplacian or something like this. We regularize the Navier-Stokes and we get our velocity in continuously from 0 to h. Then what we need to do? We again need to regularize a bit this velocity, truncate it, sample it, because it will be the one used in the minimizing movement scheme. And this is let's say, the velocity must not depend on time. So we need to sample the velocity, but now the velocity is sufficiently regular, and so we can sample it. And then we used this sample velocity to be part of the minimizing movement scheme through the flow map. So we use the flow map of this sample velocity, we put in the minimizing movement scheme, and we update. And then we repeat it iteratively, and we construct for all times a sequence of what? of the characteristic function continues in time due to the Giorgi interpolance. The W, which is the curvature potential, continues again in time due to the Giorgi. The U instead, which is the kinetic potential, which will be sampled in time, so we will need to let's say, interpolate suitably, for instance, by assuming constant values over stepwise, let's say, constant function in time. And then we have everything. We have all the objects to pass to the limit. Of course, we need a finer construction from the flow map because we need to relate in a finer way what happens to the gradients of these using some properties of the velocity, because in the end what we have is the velocity, so we need to relate everything. And then the big step is to pass to the limit in the velocity term, let's say in that truncated smooth velocity which appears in the equations in the Mullins-Sekerka part, because it's a kind of smooth velocity, so we need to pass to the limit in that. And then we also need to pass to the limit in suitable spaces, which will be L2H minus 1, also of this total material derivative discretized, which will go exactly where we want. We can pass to the limit, and then we conclude the proof. Note that, just to conclude, note that the difficulty here is that the results by Schätzle are very nice, but they're also very specific. They need to be derived from, let's say, a minimizing movement scheme, basically. So a minimization problem, because you really need some regularity properties on the sets where you want to apply, which cannot be you cannot first say, I pass to the limit in A, I make some approximation in V, I pass to the limit first in H, and then in another approximation parameter. You need to do everything at once if you want to use Schätzle results, which are fundamental if you want to preserve the Gibbs-Thompson law. So we need to find everything, so the finer scaling, so that in the end, in only one step, we are able to get all these properties. Just to conclude, so as you can see, we have included all the problems, so we treated different densities cases, we have now a sharp total energy inequality, and then we have also inclusion of the constant contact angle condition. Next steps, of course, Helmut with Wilke, they already proved the existence of local strong solution in the constant density case. Now, the point would be what happens if we consider different densities. All this should be feasible. I mean, we do not expect much complications. Of course, the operators would be probably a bit more complicated because now there could be some jumps at the interface. But let's say that this could be feasible. The new big step would be this one, so the proof of weak strong uniqueness principle. Sebastian has shown you last time that they have proven the Mullins-Sekerka, let's say the Mullins-Sekerka part, so they have proven weak strong uniqueness in 2D and then in 3D for Mullins-Sekerka. What we now expect is that our notion is perfectly feasible and ready to be shown to be weak strong unique. And this is very nice because this would mean that as long as you have a strong solution, at least in the time where the strong solution exists, your weak solution cannot create strange instability, strange singularities. It must coincide with the strong. So this means that this gives us an intuition, an idea that our weak solution in the end, okay, it's very weak, the variable is not such a nice object, but in the end, it's not creating strange singularities. It's really something that as long as you have an initial datum which is smooth, if you stay for small times, you can expect that this is really the solution you want to the Mullins-Sekerka problem. And with this, I thank for your attention.